So may we start?
Yes, ma'am.
Hello. So may we
Hello.
start? Yes, sir.
Yes, we can start.
Okay. So good evening, all the participants. We are here with the hands-on session of the FDP on recent trends on frequency selective FSS for 5G and 6G communication. So Mr. Vikram Maurya sir is taking the hands-over session. Sir, over to you, sir. Please take the session.
Okay, thank you, ma'am.
Welcome, sir.
Is my screen is visible?
Yes, sir. Screen is visible, sir.
Okay. Okay, participants. Good afternoon. In today's session, we are designing a metamaterial, and after designing this structure, after designing this metamaterial, we can analyze how we can simulate this and what are the criteria by which we can simulate this type of structure, because we generally know for any absorber and polarization converter, we are applying the uh, incident wave on the z axis. Like here in this structure, it is clearly shown. This is our meta surface, which are combined with multiple unit cell of metamaterials. This this axis, vertical axis is I will call out as z axis. So this is used as a incident wave. Means our signal is incidenting with this axis, but when we are proving this metamaterial in the previous session, one participants have doubt how we can calculate the permittivity and permeability for any metamaterial when we are designing a structure, because that part is we already know. I'm not going into that part. That our metamaterial is combined with two type of structure. One is SSR, which is a split ring resonator, which will act as a magnetic type of ring. And the second thing is the electrical wire, means any electrical patch or any rectangular shape of patch, which is used as a electrical structure. So by combining these two type of structure, we will design our metamaterial. But the boundary condition and the port which we are applying in the simulation part, this is very crucial, because for in case of absorber, it is totally different. And in case of proving this metamaterial, this is totally different. I will show you how these two things are different. So the only common part is we have to design this type of structure, which is common for metamaterial, and also it is common for absorber and PCR and filter, anything. But the simulation part, how you are applying and the uh, impedance incident signal, this is very important. I will show you one by one in CST. Just a minute. Is it visible?
Yes, sir, it is visible.
Okay. So this is the first screen which is open after opening the CST. Then the basic part we will already covered. So I will directly go to the designing part. So just choose the template. Here microwave and RF optical. Then this periodic structure. Next, the FSS metamaterial unit cell, because I am simulating the unit cell only. Then next, this is comes under the phase reflection diagram. Next, frequency domain. Next, first I will cover the gigahertz metamaterial. So the dimension is millimeter gigahertz. This is okay. Now in frequency terms, here we can put 5 gigahertz to 15 gigahertz. That you know ki, what is the minimum frequency and what is the maximum frequency for your operating band. Then next, you can also save your template by in this term. Suppose again you are not want to set all these parameters which I have already done. So you can save this template by its own for the future work. Then finish. This is the main working plane where I design. So initially, we start from to uh, upper side. So first I will design the uh, ground plane, which is a uh, rectangular strip only. It is not covering complete ground plane because I am not designing a metamaterial. I am not designing the absorber. I am just designing a metamaterial for the proving of how permittivity and permeability is negative. That's why the ground plane is not completely filled with ground plate. It is a strip of rectangular patch only. For that, just go to modeling. This is okay. I will put the name ground. You can choose the variable values also and put the values of your variable, and you can also put the direct values, what dimension you want to choose. So my dimension is minus a by 2. 2a by 2. Because I am designing this ground plane as a rectangular, that's why my x and y axes are not same. So I have to choose a different variable here. Minus b by 2 to b by 2. And this z min 0 to tg. Ground thickness. Okay. And select the material as copper because I am working in a gigahertz region. Pure copper. Load this. A value 2.5. This TG 0.035 millimeter. Okay, this is our ground. This one. See, I just remove this boundary so that no confusion will arise. Go to this view and this boundary box, remove this. After this ground plane, I have to design a substrate, which is a FR4 material, which is having a FR4 material. So again, go to this modeling. And now this substrate material is, this substrate dimension is in not rectangular, this is a square. So put this value, substrate. Now this x-axis, this x-axis is fixed, and we have to make another y-axis for this width, substrate width. Just I have to take this minus a by 2 to a by 2. This is also minus a by 2 to a by 2 because now it's a square substrate. And here we will start from TG because our material ground is end with TG. So from TG to TG plus TS. This is the total, this TS is the thickness of our substrate. Now choose material. This is a FR4 lossy. Choose this. Okay. TS thickness. TS thickness value is 0.285 minus 0.235. 0.25. Okay. Now this is the complete structure till the substrate and ground plate. Okay. It is not true to call it as a ground plate because I am designing a meta material which have two main part. One is a strip line for electrical uh, structure, and another is a circular shape of or is rectangular or circular ring shape structure for the magnetic part. So now our next target is to design a ring shape structure. Okay. This type of ring structure this this type of SSR structure we are designing here. Okay, I just give you a complete structure so that you can understand what step by step procedure I am applying for designing this type of structure. as we know, our substrate then width is 2.5. So we are making a square of 2.2 length and width. Name outer square. AB minus C by 2. Sorry. Minus C by 2 to C by 2. Again minus C by 2 to C by 2. Now our Zmin is Tg plus Ts because till now we are covering this thickness in Z axis, and our final thickness is Tg plus Ts plus Tg because this Tg is for same for the upper structure and the bottom structure. And change this material copper review C 2.2. Okay. Okay. Now this is the complete square patch, but we have to make ring of square ring. So again we are creating a smaller square patch and subtract it with outer one. We want to make a ring having a thickness of 0.2, having a thickness of 0.2. So for this, if we are taking a reference as a x-axis, then this width is 0.2 and this width is 0.2. So for overall this rectangular, this square patch is reduced to 0.4. So the next patch which we are creating, a square patch having a length of 1.8 only. So that 0.2 gap is there. So again go to brick, cut square, whatever you now minus d by 2, 2d by 2, again this minus d by 2 to d by 2, and this is tg plus ts, tg plus ts plus tg. Material is copper. Any material you can choose here because we are just using this brick or cut square shape for the subtraction point of view. Screen is not visible. The pop-up window is not visible. Okay, just a minute. Just Now it is visible. Okay. So this is the minus d by 2 to d by 2 minus d by 2 d by 2. This Tg plus Ts and this one copper. Review. D is 1.8. Okay. Like this. Because our innermost square ring is 1.8 millimeter thickness, width and height, length and width. So this gap is 0.2. We can check also. Okay, now, okay. First, I will save this template, this design, desktop only. Save this one. Now just see this. This outermost square ring, outermost square patch and the inner square patch having the same thickness. That's why it is merged. Okay. And when both the thickness are same, then only you can perform the adding and subtraction performance. Okay. Again, this is. Now, what we have to do, go to this component part in the navigation tree, then plus. Here all the four part is there, substrate and ground, this cut square and outer square. First, take this outer square ring. Okay. Then in modeling, when you are in modeling part, then go to this boolean. There are some boolean operations like addition, subtraction, intersect, insert. Okay. So outer, take this outer square, then take subtract, then take this inner square, means cut square, which I am mentioning here, and press enter. Okay. You can check its thickness. Pick point here. Pick point, then select. This is. So here all the X, Y, Z values will come. What is the for this point, this P1 point, what is the value of your X, Y, and Z at particular point? Okay. Again, take this point and choose this one, P2. And see this P1 minus P2, it is 0.2. That means this thickness is 0.2. Okay. Now come to next part. Now we have to make a now we have to make a cut here in the left side. if you know the parametric value of this, what variable you are assigning here or here, and what length you want, then you can directly use it. Otherwise, you can put a random value for making a structure so that we can remove this part. I will show you. Again, go to this brick. For this ring, if we double click it, then this is the outer ring. Go to this edit part. This variable is C. Okay, C by 2. This is C by 2. And the subtraction part is D by 2. Okay, done. Go to this break. But what is X min? X min is, because I am in the left side of this structure, that means we are taking all the values in negative manner. Okay. So the X min value is minus C by 2. And X max is minus D by 2. Y min, what thickness value of cut we want. How much is the width of this cut, this one, that we have to choose. So if it is minus X by 2, X by. This is again PG plus TS. PG plus TS plus PG, copper plate, review, X value 0.15. Because I want in the Y axis, I want 0.3 mm width for the cut. That's why I choose this minus 0.15. In the negative axis, minus 0.915. In positive side, 0.15. So the total thickness will be, so total width will be 0.3. Okay, this one. This is 0.15. So I have to change this axis 0.3. If any instant of time you are changing any variable expression value from the parametric list, from this parameter list, then you have to press the F7 key. This one. Okay. Again, go to the outer square, then go to subtract and cut, enter. In a similar manner, we have to make a second square ring and then cut a patch here, this side. So I will do it. I will do this part in a fast manner so that because we already know how can we make this square ring by using a square patch and then cut. So we can create a square ring. So I will do this part directly without giving a variable. I will directly put these values. This one. Okay. Okay. Now we have to first choose this one and then go to the subtract, second square cut, enter. So the second square ring is created. After that, we have to make a cut in this area. For that, and the cut length and width are same. The length and width is same, which we are creating here. So we can directly take these value and put it here. Otherwise, just a minute. See, there are two options. One, I will show you both the manner. First thing is just see the dimension of this cut, which you can see here. This one. Okay. Create this one and make a mirror of this structure so that you can, no, you have to make, sorry. What is the value of this? Minus 1.5 by 2. Okay. And what is the value of this? 0.55. Okay. Now we are making a structure in the right hand side. So our all the dimensions are positive here. In the right side, all the dimensions are in positive way. So x min is 0.55, x max is 1.5, y min x only. So minus x by 2, because this is same in the y-axis. This is this one. Just something went wrong. Not 1.55, 1 point. Okay. We can directly give this value on, because x min is 0.55. This is this value. The inner square 0.55, and I know our ring width is 0.2. So I just add 0.55 plus zero point 0.2. So I will come in this side. Okay. Now all the part, rest all these. Right. Okay. Then go to these. This note. This one. Subtract. Last cut. Enter. This is the complete metamaterial designing part. Okay. There is a strip. There is a substrate, and then two SSR structure, split ring resonator, square shaped. We can also make a circular shape split ring resonator also. Now the designing portion is completed. So the next part is to give the boundary conditions and excitation ports. So for that part, we have to know where our resonating structure is placed. Just see. Focus on this axis, this one. This is our x-axis in the horizontal manner. This is our y-axis in the vertical manner, and the screen direction is our z-axis. Okay. But see this. This strip is in the x-axis. Okay. So first I will change the direction of this metamaterial. Just a minute. We can also make in this manner also, but it is more easy to understand like this. Okay. I will put my structure in such a way that this backside strip, this one, backside strip is placed in the x direction. This is the pan view, so we can shift anywhere. This is the rotation. Okay. Now see, our magnetic structure is on the z plane only, this upper side, because this is our z axis from the screen direction, this one. Upper to lower side, z min, z max to z min is the direction for our magnetic ring. This two square ring is act as a magnetic ring, which is responsible for giving the negative permeability for this metamaterial. Okay. And in the bottom side means in the direction of x, our rectangular strips are placed. which is responsible for the magnetic. This is responsible for the electric strip, which is useful for giving the negative permittivity for this metamaterial. Okay. By seeing this term, we are placing our boundary conditions. So for that, go to the simulation part. Okay. First check the frequency 5 to 15. It is okay. No issue. Boundary condition. It is already there. You can check the boundary condition. No issue. Simulation. This boundaries. If you directly put the unit cell in the x-min and y-min direction, and this z-min and z-max you will putting as a open add space, then that condition is used in the fluctuate port condition. And we are using this type of boundary condition for our polarization converter and absorber case. But for proving this metamaterial, you have to select this Z min, because in the Z axis, I will already told you, in the Z axis, our magnetic, this rings are there. So Z min is magnetic as tangential component of magnetic is 0. Here also, this we will place Z min magnetic. Okay. We know in the X axis, I have already shown you in the X axis at the bottom side, our strip is there. So we have to place our ET0 term. ET0 in the X-min and X-max direction. Clear? Now, the third part, Z-min and Z-max. This one. This green color is shown as a Z direction, Y direction. This is our Y-min and this is our Y-max. We have to place a waveguide port in the Y direction. Okay. For that, we have to open it. No need to put ET0 or HT0 here. Just open. Here also just open. If you are placing open space, then it will create a space between your port and your material, because your material is starting from here and your port is starting directly where your structure is ending. That's why, because I am choosing Wyman open. If I am choosing open add space, see, this is the space. The term add space is this. Our port is placed here and there are some space in between our port and our designed structure. And after that, our structure, and again this side, we are directly choosing the open boundary condition. That why it is starting directly at the end of this. If we are placing open add space, again it will create a space between your port and your structure. But we have to place our port directly at the end of this structure. So open and open. This is the boundary condition which we are applying. We are not applying the waveguide port. So first we will choose and see this fluctuate boundary which are earlier showing. When we are choosing the X-min and X-max unit cell means we are creating a periodic boundary condition. At that time, fluctuate boundary port is already assigned. But here, no simulation setup are there. So first choose this type of boundary condition, then click OK. Okay. Now, one thing is clear, we have to place our port for the excitation in the Z direction only, in the direction, because in the Z and in the X axis, our structure are ET0 and HT0. See this port in the navigation tree, there is a term port and no port are assigned till now because we are not creating a port. So go to this waveguide port here. For any FSS and metamaterial and polarization converter design, you can give them excitation using a waveguide port or using a fluctuate port. Fluctuate port you can directly assign by choosing the boundary conditions which we have applied earlier, and for the waveguide port we have to assign separately. So now go to this waveguide port here. Initially it is showing port in this direction, means in X direction. See, because this is our X direction, this is our Y direction, and the direction of this design is vertical direction is Z. So by default it is showing here, because in this waveguide port, we are clicking this X, and you can choose your port direction X, Y, Z from here. Okay, and two things is there. For any axis there are two things, one is positive X and one is negative X. So in the X axis, if you are choosing your orientation as positive, then it will uh, place the port this plus Z direction, and if we choose this normal X axis and orientation is negative, then it will create your port here. Okay, but our target is to place our waveguide port in the Y axis. So just choose this Y. Okay, first choose this positive so that the first port is assigned here. In the negative X axis, so positive and apply. See here in the port, there is one plus term, port 1 is assigned, and in this Y axis, go to this negative term, orientation, and also assign, or just want to apply, or click directly OK button. Now both the ports are assigned, this one and this one. See, port 1 is from there to here, port 2 is from here to here. Okay, now ports is assigned and the structure is already designed, and we have put the frequency value range. Boundary box. Now one more part is remaining. Just see, this is my port 1. Okay, and it is covering exactly the same width. Sorry, here. This waveguide port is covering the same width which we are, what is the thickness of our structure, covering entirely in substrate, then ground, then this resonating part, and also for port 2, which is covering the same width. But we have to choose a little bit large thickness of this port. So where we can change this? I just done this so it is clear to all. This is the exact direction. Okay. This is the direction. The simulation part, background. This is the background. Here this lower X surrounding space. See this term, surrounding space. Lower X distance, upper X distance, lower Y, upper Y. We don't have to change this value because we have created a ET0 and HT0 here. Now this lower Z direction and upper Z direction, just make a 2 or 3 millimeter, means little bit extended port in the both the directions. So 2, 2. Okay. See, now our port is assigned. Port 1 and port 2 in the Y direction, ground and upper, all are completed. Just simulate it. So go to the home and start simulation. Oh, sorry. Setup solver. Go to this setup solver. All port. Or you can choose only port 1 or only port 2. All port. Start. It will hardly take just 1 to 2 minutes. The simulation is completed. First check the S parameter. See, this is the S parameter which are coming. It is not the absorber's result. Okay. So it will not come below -10 or that whatever you see at the absorber point of view. The only thing which we are seeing in this metamaterial is when we are taking this S parameter, means all the 4 parameters we are seeing together. This S11 and S22 is similar. This is S11 and this is S22. Because in both the way, when we are putting your here, when we are putting the uh, incident signal from port 1, and whatever is reflecting back at port 1, and whatever we are putting at port 2, and what portion is reflecting back at port 2, both are similar, and the transmissions are also similar from port 1 to 2 and port 2 to 1. So that's why our S11 and S22 are equal. This will show you the symmetricity of the structure. And this S21 and this S12, both are also similar. But here the phase. Open all these things. When we are seeing the phase of these S parameter, then there is a change in phase from 10 gigahertz, or if we see the exact value, means we can see from 10 gigahertz to 11 gigahertz. Roughly we can say from 10 to 11 it is changing the phase. So our metamaterial is working properly in this region only. Okay, from 10 to 11. This is we can observe by seeing the S parameter of this structure, because phase is changing from here to here and here to here. Now we have this S parameter, so we can directly calculate its permittivity and permeability values, which is important for metamaterial. For that, after simulating the structure, when we got the S parameter, there are a term, this after this simulation, this post processing, all the terms are in a series way. Means first you have to model your structure, then you have to simulate, and in simulation first you have to adjust these three things, then you have to choose the port of your port, which port you are applying, and then you have to simulate your structure. And after simulating, if you observe your S parameter and 1D results, or you can also see your 2D results also in the field monitor, which we will cover later. Then this post processing means after processing. Go to this post processing term, result template. Go to this result template, and you have your S parameter. There are multiple options. In case of absorber, we are in case of absorber and any type of structure, we generally choose this general 1D. We are choosing this general 1D, and then we choose this mixed template results, and here we are putting our formula for PCR, for absorber, for impedance also. Means if you already know, if you have your S parameter S11 and S22, S11 and S21, then you can directly calculate your impedance also. So you just need to put your equation here. In case of absorber, you have to put absorption equation here, but in this case we directly calculate our permittivity and permeability. Just go to this S parameter. In the upper section, you have to choose this S parameter, and here see multiple things are there, but this extract permittivity and permeability from S parameter. Just tick this term. Okay, it is showing now S11 equal to and S21 equal to, means you have to select your value. Multiple results have there, but you have to choose what is S11. It is already written as parameter slash S11. Just check this. S21. Whether you have to choose S21 or you have to choose S12, both are similar. So whatever you want, you can choose. So I'm choosing S21. Then this is effective thickness of material sample. Means what structure you are designing. What structure you are designing, just put its effective thickness, means complete thickness. What is the value of what is the thickness value of your substrate, plus what is the thickness value of your ground, which is uh, rectangular strip, and what is the thickness of your upper square ring. The complete calculate all the three values together will define the effective thickness. So what is the complete value? See, this TG is 0.035 and this TS is 0.25. Okay, just calculate it. 0.25 plus 0.035 plus 0.035. Enter. 0.32. 0.32 is the complete thickness of your material sample. Put this 0.32 here. MH0. Okay. Now okay. Now you put all these things, then simply evaluate. Simply evaluate the term. Okay. And if you are doing multiple parameters, means before calculating the S parameter value, before calculating this permittivity and permittivity value, if you have multiple S parameter value, then you have to take this evaluate all. Right now I have to evaluate only because there are only one results. Evaluate. Okay. Just close this. See, initially in this navigation tree, there is a term 1D results. And in this 1D result, I am opening this S parameters and I have seen all these four S parameter value. But at the end of this, there is a table term. Just close this one. Tables. Okay. Just go to the plus 1D result and the complete extract material properties are here. So our target is to see the epsilon r and mu r value. This epsilon r is the permittivity and this mu r is permeability. Okay. First I will see the epsilon value. Just see this. This real and imaginary part, the complete real imaginary part is below 0 means negative. This structure is showing negative permittivity value from starting 5 to around 12.2 or whatever. If you want to see the exact value of this, then go to the cursor marker here in 1D plot. In 1D plot, just go to this cursor marker, add curve marker. Okay. And directly you can press the M key and you can put your cursor wherever you want. Marker. Okay. You can choose from here also and go to your double click here. This marker will show you the value 12.33. 0 point means negative value. Minus 0 point is this. Just zoom this. just zoom this value. See, after zooming it, we have to put our marker here where this will cross the zero line. This one, this. So place your marker here. Again, press the space key so that initial curve will come. So the exact value where the till 12.37473 gigahertz, our structure is showing negative epsilon value. Okay, this is clear. Now this mu r. First we will check the mu r. This is the mu r value. Okay, starting from 5, it is showing, starting from 5 gigahertz, it is showing positive permeability value. And after this term, this 10 point, we can also check its value. Just press this M key. Okay, from here to here means, and after this 11.166 gigahertz, 11.166 gigahertz, it is again showing the positive permeability value. That means the structure which we are designing is showing the negative permeability value from 10.1807 gigahertz to 11.16642 gigahertz. Okay, this uh, operating band is only for permeability, and this operating band is for permeability. But after combining these two, means after clicking the control button, we are selecting both the term. This one. So it is very obvious that from this, no need to check this first marker, because after seeing this third marker value, which is 11.166, the structure is showing positive permeability value. That means from this to this, sorry, from this 2 to 3 means 10.1807 to 11.1642. Just to write these values. 10.1807, 11.16642. From here to here, from this to this range, our permeability value is negative. Also, our permeability value is also negative. Both the term are negative in this term. That means it will act as a perfect metamaterial, which we called as DNG, double negative material. We already know our metamaterial is divided into 4 terms. ENG, DNG, SNG means only single negative, no negative. So it is behaving as a DNG, double negative. Epsilon and mu both are negative. And if we know if our epsilon is negative and if our mu is negative, then the refractive index N N is also negative in this area from 10 to 11. It is also negative. And that's why our S parameter, when we are initially, when without checking our permittivity and permeability value, when we are directly checking our S parameter, within this range, within this operating range, our structure is showing the uh, phase reversal, because structure is behaving as a metamaterial in this area. Okay, this is the complete uh, study of the any metamaterial structure. So these all are the parts which we have covered in this session. Just design the structure, then we have to simulate this structure in this way as a metamaterial. Okay, as a metamaterial we have to simulate it like this only, and then our result will come like S parameters is behaving like that. This is phase changing will occur from 10 to 11, and simultaneously when we are checking its permittivity and permeability value, it will also showing the same phenomena within this range only. Okay, this is the concept for metamaterial. And I'm not, because at any case, suppose we are simulating this structure and we got all these results. Now if we want to change our port position, suppose we know we are making these design, and now we don't want to simulate it, or we don't want to excite it from the mm, y axis. We want to simulate it by incidenting the signal from the z axis. Okay, if we want that, if you change the port or change the boundary conditions directly in this structure, then the previous results which you are already achieved, that will delete. Okay, so the best way is save this, just save this result and make a copy of this structure only. No need to save, no need to copy the result part, just copy the CST file. Okay, this is the structure, this is the CST file, and the upper one, this is the FSS folder which is carrying all the result part. So I just copy this, just change this name, testing. Okay, I just make a copy of the CST file only, open it, because I don't want to delete my result at this time. That's why I am making another file, so I can do anything. Now see, only the designing and the boundary conditions are there. No results are here. In 1D results, there are no any result. In table, no any results are here. So just put it like this. Okay. Now I want to remove this port. Delete, delete. Port 2, delete. Yes. Okay. Go to the simulation part. This frequency term is okay. This boundary condition is okay. Now go to this boundary. This is already applied, which we are done in the previous file. Now here I am making it as an absorber, because I don't know whether it is working as a proper absorber or not. Maybe there is some modification is required, or maybe some optimization in these structure is required. Mm, I mean to say the width, the thickness, the gap between these touring, the gap between the outermost substrate and the first ring, maybe some modifications or some optimization is required, but we will just check. We will just clarify you key what are the changes we have to do when we are doing simulation in terms of metamaterial and when we are doing the simulation for the absorber point of view. For that, we have to select the boundary. Here we come. Then in case of absorber, we want a structure as a periodic. So we want in the x-axis and y-axis, our structure is making a infinite periodic uh, surface. That's why in the x-axis, as I click this x min as unit cell, the complete x max, y min, y max are unit cell automatically. Say this because he already know you want to make a boundary periodic structure. So the x min is unit cell, x max is unit cell, y min is unit cell, y max is unit cell. Okay. So this structure is, this surface is completed. Now we have to change this z min and z max. Okay. And see, after choosing this x min and x max as a unit cell, this is changed as a fluctuate boundary. So now we want to put our source, whatever source we are applying for incidenting the signal, which we have to put in the z direction. That's why, and we want some space in between the uh, structure and the source. That's why I'm choosing this open add space here and open add space here also. See the structure. This is the term. This is the schematic view of this fluctuate port structure, where the surface is act as a FSS structure, and we are applying a fluctuate port in unit cell only for simulating our designed structure. Okay, I know the structure is not behaving like a absorber because the ground plane is not completing ground, and the upper resonating structure also want, yeah, or need some modifications, but we are just checking it. After doing all these boundary conditions, after applying all these things, just tick OK. Now see, when you are in the navigation tree, when you are pick this Zmax term in port, this is Zmax, means your signal is incidenting from Zmax port and it will goes to Zmin. Okay, Zmax to Zmin. These all are very important terms which we have to know from where we are applying our incident signal and from where we receive our incident signal, which port we have to close as a ET0 and which port we have to close as HT0, that we all know. We have to know all these things. Okay. Port is Zmax, Zmin. Yeah, correct. Now just go to home and first go to the setup solver. Just check here in the frequency domain solver parameters. The fourth one, that this excitation term is there. In the excitation, it will ask source type, and the source type is 4 type of source. We are not using list here. We just use all fluctuate, or we are just mentioning it whether we have to put our excitation source in Zmax direction or only in Zmin direction. This is for only one type of direction. But all fluctuate means it is simulating in both the direction. Means in one time it will set its source in the Z max direction and another time the vice versa. Okay, all source put it here, and it's up to you whether you want to adapt to mesh refinement or you have to untake it. Start. Now these all setting is for uh, any structure, whether it is absorber or it is polarization converter or filter. And I am doing this simulation for a single unit cell. That's why I am applying the fluctuate port. It is taking 2 to 3 minutes. Okay, as simulation is going here, just go to one question is there while simulating whole part of structure, which type of excitation is used? Right now, for the case of absorber, I am using fluctuate port excitation for simulating the absorber. And at the time when we are making and designing and analyze the metamaterial thing, then we are doing our excitation by with the help of waveguide port excitation. And in both the case, the source is gigahertz. Yes, structure in the this metamaterial. If we assume that this part, our structure is resonating, the resonant frequency is this. Means suppose it is 10.5. Sir, please show how the array or full structure is simulated in CST. That we will cover in the next session, Abhishek, because it is already 7, 5, 10. No, I have already planned for this. Okay. Yeah, conformal will also be cover. Step by step, we will going when as we are going forward, we will cover all these things. In the first lecture, we are simulating the metamaterial and proving the metamaterial, how the permittivity and permeability behave, and then our next target is in the next we will cover the absorber point, all the absorber point of things, and in the absorber, we will cover your topic, which is how the array and the full structure is simulated in CST. Okay. And further, further, we will cover some PCR, polarization converter, whether it is reflective type or transmittive type. And then finally, we will cover this conformal simulation. Any structure you can bend, whether you have to bend it in a in a positive angle way and in a negative, means in a concave type of structure or in a convex type of structure. That all we have covered. Okay, back to this structure. For this FSS metamaterial, if we uh, 10.5, okay, this is 10.5. So if we want to check its electric field or surface current, then just close this result, then go to the simulation part. Okay, in simulation, can we have the recording of your session? Yeah, it is already saved in the YouTube channel. We will send you the link of that playlist. You can see all that, all the session and in the evening session, all are saved in YouTube channel. And we have also the recordings, which we will share you at the end of this FDP. Okay. Now this field monitor. Automatically it was closed. Just a minute. Actually, it is taking some time. It is not simulated properly. See, it will take some time. So if you are also designing this thing, and if you are applying this type of fluctuate port or this type of boundary condition, you can simulate it by its own, and you can check how much RAM is needed to mainly needed to simulate FSS full structure. Yeah, when you are simulating it as a FSS as a array structure, then more than 16 GB RAM is required because it is taking so much of time. And if your structure is having a large operating bandwidth, then it is also a problematic. Not only RAM, the processor and everything is required. So my suggestion is don't run it in your laptop. Use the system for the array type of structure. I am not simulating this structure, which I am applying as a FSS. Just simulate it. Wait. And if you know the exact value of, and if you know the value of your resonating structure, means what is the resonant frequency of your structure, then no need to put a large value of your operating bandwidth. Like suppose I know my simulation, in my simulation, my resonating frequency is around 10 gigahertz. Suppose I'm just letting, suppose my resonating structure is resonant frequency is 10 gigahertz, then no need to simulate it from 5 gigahertz to 15 gigahertz because it's a wastage of your time and the wastage of your simulation setup and your laptop also. Yes, it is mainly due to the 16 GB RAM. You can try one thing, just go to your temporary file and delete all the temporary files from your computer. And after that, you can restart your system and then again try. For gigahertz, I am doing 3 cross 3 structure, 5 cross 5 and 7 cross 7. So I got the results. So you can also, means uh, in my opinion, 7 cross 7 array structure you can simulate for this 16 GB RAM system. I think is it taking so much time. So if you have any other query, you may ask. Yes, Abhishek.
Hello.
Yes, Abhishek.
Sir, can you hear me?
Yeah, I can hear you.
Okay, sir. Very good afternoon, sir. A nice session by you. Actually, I am Abhishek
Thank you.
and research scholar from BITS Pilani.
Yeah, I
Actually, I
know.
am working in the field of this FSS. Um,
Okay.
when I simulate this Fabry boundary condition, we are characterizing in that or having measurement in the lab, like two horn antennas are there and in between there is an array of FSS.
Mm,
So
okay.
how to simulate that in CST, two horn antennas and in between there is a FSS structure.
But why you have to put two horn antenna
uh, I
in
I want
in
to
the lab?
uh-huh. Because
In
in
the lab,
many papers I have seen that they are doing this using
yeah.
Fabry boundary conditions. Something I don't know what is that Fabry boundary condition. So I want to know
But
that. Hello.
but the results are almost similar.
For unit cell.
No, for FSS array, because suppose when you are designing a unit cell structure, okay, and
Okay.
you are simulating it, then
Mm-hmm.
you got some result, okay,
Okay. Yes.
but when you are designing a array for that unit cell structure,
Okay.
okay, you are creating I will tell you in next session, when you
Mm-hmm.
are creating a multiple unit cell to make a FSS array, whether it is 5 cross 5 or 7 cross 7 or 11 cross 11,
Okay.
in that manner we have to create in a
Okay.
odd value,
Okay.
okay, then fluctuate port is not useful in this case,
Okay.
because if you are making a array of 5 cross 5 and then you are mentioning it as a fluctuate port designing or unit cell boundary condition, then the whole 5 cross 5 is act as a unit cell,
Acting as a unit cell. I know
and
that. Yes.
yeah,
Yes.
and then it will create a array of multiple array of
Ha.
the your structure,
No, no,
okay,
I'm not
then
doing
it
that.
is very
I'm not doing
complex.
that. It will become very
Yeah,
complex and
okay,
it will go out of memory.
yeah, this is the
Ha.
first thing.
Okay.
Another thing is, another thing is your question what you ask. So for array structure,
Yeah.
you can use the waveguide port.
How to do that? I want to learn that. How to assign waveguide port
Yeah,
on X direction or Z
tomorrow
direction? I will
in
attend
the
the
z
session
direction
tomorrow.
only, in the z
Z
direction
direction.
only, in the tomorrow I will show you ki
Okay. Okay.
how we can simulate the array structure by using the waveguide port in the zmax direction, because
Okay.
if our structure is placing on the zmax direction, then the thing which you are asking about the horn antenna, horn
Okay.
antenna is what? Horn antenna is like a port which you
Uh-huh.
are applying in this CST.
Yeah.
Okay. In the fabrication lab, in the testing lab, or in the anechoic chamber, two
Yeah.
horn antennas are used. One is
Yes.
placed in the ZMAX direction and
And
one is
another
placed in the ZMIN
Z-min direction.
direction.
Yes.
Okay.
Yes.
So that means the ZMAX direction, the antenna which are placed in the ZMAX direction, that will be act as a transmitting antenna
Transmitting,
that
and the
will
other one will
transmit
be.
the incident signal.
Yeah.
Okay, and
Yes.
the other horn antenna which are placing at the back side of this surface, this will act as a receiving antenna, or the
Okay.
first antenna is also act as a receiving antenna. So
Okay.
when you are calculating the S11 parameter, you
Mhm.
directly calculate with the first antenna only.
Yeah.
Okay, and when you are calculating the S21, means how much how much transmission will take place, that you
Yes.
will
Yes.
calculate with the help of judgment
I,
side of your horn antenna.
yes. Yes.
So
Yes.
there is means you have to no need to make a different horn antenna and then your structure and then simulate it. When you are
Okay.
placing a port, it will also act as a horn antenna and behave like similar type of results will come.
Okay. Okay.
Very
Okay.
less, there are changes, there are a little bit change will occur, but that will work.
Okay. Okay. I will
The waveguide port I
definitely
will tell
watch.
you tomorrow.
Okay, okay. And one last question is that
Yes,
what
sir.
will be the size of that array? You said that 3 cross 3, 5 cross 5.
Yeah.
How to decide
Mm.
that size? Whether I go for 3 cross 3, 5 cross 5, because in reality or in a practical application, when we go in the laboratory, we mainly manufacture a 30 cross 30 centimeter. 30 centimeter, 30
Why
centimeter.
you are creating the designing the 30 cross 30 structure?
Like that when
It
I
depends. It
huh?
depends. It depends
So
on your frequency value.
okay, like
Suppose,
my
suppose,
FSS is working in X band, like 10 gigahertz, suppose.
Yeah, that you have to calculate. So if your antenna, if your absorber is working at X band, that means it will cover a 8 to 12 gigahertz frequency.
Yeah, yeah.
And if your absorber is working on a 8 to 12 gigahertz of frequency, then you have to place your antenna accordingly in the anechoic chamber.
Okay.
In
Uh,
simulation, it will run directly. Okay.
okay.
By applying the port, it will run. But
Okay.
in the fabrication lab or in the anechoic chamber,
Uh-huh.
with the by the help of with reference to your frequency, you have to select your horn antenna. Which size of
Okay.
horn antenna you are using?
Huh.
Okay,
I'm using
okay.
X-band horn antenna, 18 dBi, the
You are
standard
using
one.
X band horn antenna, and
Yeah.
for that, the difference, the distance between your transmitting and receiving, and in between your structure, this is also fixed.
2D
You
square by
can't
lambda.
randomly.
No. The distance is 2D square by lambda. A far distance, far
Yeah.
field distance.
Yes. Yes. So
Okay.
that means you are placing your structure with reference to your antenna with a particular direction, particular formula, and a particular distance. Okay.
Okay. Okay.
Now this D is the opening of your horn antenna.
Yes. Yes. Aperture. Huh.
What is D? D is the maximum opening area of your
Huh.
any
The
antenna, no?
diagonal one. The diagonal one.
Diagonal one, the maximum dimension.
Yes. Yes.
That what that will define.
That is
Why
the
we use
capital
this
D, na?
D only?
Capital,
Why we will?
the maximum size of the aperture we
No,
have to
no,
take.
no. What is the use of this D in your far field calculation formula? What I
Mhm.
am that I am asking.
Sorry,
Why
sir.
only D?
I
है
don't
ना,
know.
that you know don't know. So
Yeah.
that's why I am telling you. The this is the opening of the horn antenna is called as flaring effect. Flaring.
Okay. Okay.
Okay. The what is horn antenna? Horn antenna is a simple mm, waveguide. Okay.
Okay. Yeah.
And the flaring of that waveguide will allow it to radiate.
Yeah.
Okay. So
Yeah.
the value of this D will define your structure, your incident signal will cover how much of area
Okay.
in the free space.
Okay.
Okay.
Yeah.
And
Yeah.
based on that opening and covering area, you have to design your surface so that in a particular direction, complete signal will incident on that surface only. If you are placing a smaller surface, so some part of signal will directly come from source to directly go to your receiver side.
Receiving receiver
Without,
side. Okay.
yes, that
So,
is the funda you have to calculate.
can you show me that one example in your upcoming lectures, or
Which example?
like this one example, that we are having an X-band antenna, and how much
Okay,
size,
okay, okay. You want to say ki okay,
or
okay.
any
Means you want,
video or any reference that I can read from YouTube, or any literature survey,
yeah,
any.
I will give you the reference paper. For that, you
Okay,
can calculate these things and you can apply it in your project. Okay.
okay. Thank you very much.
Okay. Thank you for your content. Okay.
Okay, welcome.
Any other query? Hello, Swati ma'am.
Participants, if you have any query, you may ask. Sir, I think there are no more queries right now.
Okay, ma'am.
So, thank you very much, sir. The session was very much fruitful.
Yeah.
And participants, if you have any query, you can ask. No, sir, I think right now there are no queries at present. Thank you very much, sir.
Sir, can you provide your
Thank
email
you.
ID, please? Hello.
Yeah, I will give you.
Okay, sir. Okay.
I will just post it in WhatsApp group.
Okay, sir. Okay. Okay. Thank you.
Dear
Okay.
participants, next session will be tomorrow at 9 a.m. sharp. You are kindly requested to join on time, sir.
Thank you. Thank you all.